Today we're going to learn about the Ductile Coulomb-Mohr theory. Now, Coulomb was a French officer, engineer, and physicist, as well as the father of electromagnetism, who was around in the 1700s. And Mohr was a German civil engineer, professor, and a great contributor to stress analysis, active in the 1800s. Between these two scientists, the Ductile Coulomb-Mohr theory was developed. The heart of this theory is that yielding can be determined by taking the results of a tension, compression, and torsional shear stress test and using them to construct three Mohr circles that define the failure envelope of a particular material. So the idea is to do tension test, compression test, and shear stress and combine them to figure out how a material responds to a complex state of stress. Now, this theory works best, or is best, most useful for materials that exhibit tensile-compressive asymmetry. That means when the compressive strength of a material is not equal to the tensile strength. Now, for example, here we have a plot of an additively manufactured margin steel. And for this steel, tests were done in tension and tests were done in compression. And we are given both the true and engineering stress strain curves here. We can see that there is a difference between the tests that were done in tension and the tests done in compression. Not only is their ultimate strength different, but their yield strength, the 0.2% offset yield strength in tension and compression, are also different. So then how do we manage, if we say are given a state of stress, a stress tensor, being able to predict when this structure will yield, right? That's where our theory comes into play, the Ductile Coulomb-Mohr theory comes into play. Let's also consider concrete. Concrete is a material that exhibits tensile compressive asymmetry, where the tensile strength of concrete is only 10 to 15% of its compressive strength. That's why most civil engineered structures, we try to design them to be in compression because they're much stronger in compression. And we want to avoid tension as much as possible in bridges and other civilly engineered structures. So the Coulomb-Mohr theory is based on three simple tests: a tension test, compression test, and a shear stress. We take those tests to yielding, or we can take those tests to rupture and define the yield surface or the rupture surface. We go ahead and take those experiments and plot Mohr's circle for each test and bounding curves to find our failure envelope. So we define some bounding curves in our state of stress. And important thing to note, in the Ductile Coulomb-Mohr theory, we assume that that boundary is a straight line. Now, graphically, this failure theory can then be derived as the following equation, where Ductile Coulomb-Mohr criterion, the first principal stress divided by the tensile strength minus the third principal stress divided by the compressive strength. If that is greater than or equal to 1, we are yielding, or we are on our failure surface. If we wanted to add a safety factor, we'd simply replace the inequality with an equal sign, and then the right-hand side with 1 over n, where n is our design safety factor. Now, generating the yield surface, actually drawing the yield surface for this theory, is fairly similar to the other cases we saw. We will define three cases: a case where sigma A is greater than sigma B, and they're both greater than 0. And we'll find a straight line expression where sigma A, if it's greater than or equal to the tensile strength, then yielding or failure occurs. Case 2 is when sigma A is greater than 0 and 0 is greater than sigma B. In that case, we go ahead and get our full theoretical equation, which is a straight line, which is bounding here. And then in case 3 It's when both principal stresses are smaller than 0. So sigma b, if that is less than or equal to negative the compressive strength. So we get a straight line here. And with these three cases being symmetric, we can then form an envelope, so find the companion sides, and now we have our yield surface or failure surface based on ductile Coulomb-Mohr. If we do a little bit more work to find an equivalent torsional yield strength based on the ductile Coulomb-Mohr theory, we'll find that the torsional yield strength is equal to the tensile yield strength plus the compressive yield strength divided by the tensile yield strength plus the, well, that doesn't look right. Something wrong with this equation. So we'll provide an updated one. I'll have an update in the comments. So that's it. We're done with the ductile Coulomb-Mohr theory. Now we'll move on to iron brittle theories.